Hello everyone, welcome back to MP Coding. This is the next video in our FreeRTOS synchronization primitives series. And today, we're going to talk about event groups. If you're new here, I recommend watching the previous videos in this series first, so you'll have a solid understanding of the concepts we've covered so far. Alright, let's get started with today's topic. An event group is essentially a collection of bits that tasks can wait on. A task can block until one or more specific bits are set before it continues execution. This is extremely useful for synchronizing multiple events. For example, you can have a task that waits until both the Wi-Fi connection is established and the sensor ready flag is set before proceeding. Now, let's jump into the STM32 example and see how this works in practice. Create a new STM32 project. As before, I'm using the STM32 F429i Discovery board. I won't use the board's default configurations. I'll start from a clean slate so we can set up only what we need for the event group demo. Okay, first I'll clear all the pins. Next, open RCC and set the HSE to the crystal oscillator. In the clock configuration tab, this board uses an 8 MHz crystal, so leave the HSE at 8 MHz, select HSE as the clock source, and push the core up to the maximum frequency of 180 MHz. Now go to the middleware FreeRTOS section and set the interface to CM-sys-v1. I won't define the mutexes, timers, or event groups here in CubeMX because, as before, I'll use the native FreeRTOS API in code, but I will show a couple of CubeMX settings that are helpful for event groups and ISR usage. First, in the Config Parameters tab, enable Use Timers. That because in event group examples, ISR deferred work use the FreeRTOS timer service or the timer task to safely defer work from interrupts. Enabling timers creates the timer service which lets you schedule deferred actions reliably from ISRs or tasks. Leave the timer task priority and timer task stack depth at their defaults. Usually the default values are chosen to be safe for typical use. The timer task only runs briefly to process timer callbacks or deferred work, so the default priority and stack size are appropriate unless your application has unusually heavy timer callbacks or strict real-time timing requirements. Next, go to the Include Parameters tab. First, enable xTimerPend function call. This enables the API that lets ISRs pend a function call to be executed by the timer task. Then enable xEventGroup setBits from ISR. This enables the ISR safe variant of the API to set event group bits from an interrupt. Why enable these? Because ISRs must never call normal task-level FreeRTOS APIs that may block or are not ISR safe. These two APIs are explicitly designed so an ISR can safely request deferred actions or set event bits without breaking kernel rules. Later I'll show what CubeMX adds to FreeRTOS config.h for these settings and the generated stubs. That's all for the RTOS setup. Next, go to Connectivity and set UART1 to asynchronous mode. This board's virtual COM port is connected to UART1, so we'll use UART1 for serial messages and logging. Configure your GPIO pins for the logic analyzer outputs, the same pins I used in the previous videos. For the external interrupt, set PA0 as a GPIO external interrupt. That's where the board push button is connected. In NVIC, enable EXTI0 and set its priority to 7. I set it to 7 so this interrupt is a kernel-safe priority, below the maximum syscall interrupt priority used by FreeRTOS. It's configured so the ISR can call ISR-safe FreeRTOS APIs without violating the interrupt priority rules. Finally, in system change the time-based source to a hardware timer other than systemtick. Systemtick is used by the FreeRTOS kernel. I'll pick TIM6 for the HAL time base so there's no conflict with the kernel tick. Okay, that's everything. Let's generate the code. I'm not going to use the CM-sys layer for this example, so first let's include the native FreeRTOS headers. Open the cm-sys-os.h file and copy the FreeRTOS include lines. Then in main.c remove the cm-sys-os.h line and paste the native FreeRTOS headers instead. One of the headers we need is the event groups header. Open it and you'll see the functions related to event groups. xEventGroup create function creates an event group. xEventGroup wait bits blocks a task until one or more specified bits are set in a previously created event group. xEventGroup setBits sets bits in an event group. Setting bits will automatically unblock any tasks that were waiting for those bits. xEventGroup setBits from ISR, the ISR-safe variant that can be called from an interrupt service routine. Also take a look at the other functions in this file, they'll give you a fuller picture of how event groups work and how to use them in real code. Okay, let's start coding. As before, I'll remove the CubeMX generated default handles and functions that we don't need. I have already written the code, so let's take a look. I've created an group event and tasks handles. Next I define the event bits. Event bits are stored in a 32-bit type, so we can use up to 32 separate event bits in a single group. For this demo I only need 3 bits. 0th bit for task 1, 1st bit for task 2 and 2nd bit for task 3. I also defined all sync bits as the combination of all tasks bits. And here are the task functions. In main, I create the event group using xEventGroupCreate, and store the return handle in GroupEventHandle. I print the result over UART so you can see whether creation succeeded. Then I create the tasks with xTaskCreate. Here I won't going to re-explain the parameters since they're the same as in my previous videos. The 3 worker tasks are created with equal priority, and the watchdog is created with a higher priority. Finally, we start the scheduler with vTaskStartScheduler. Alright, now let's inspect the individual task functions and see how they set and wait for bits in the event group. Task 1 toggles GPIOG pin 13, then sets its event bit using xEventGroupSetBits. This indicates to the watchdog that the task is alive. Finally, it waits 1 second before repeating the cycle. Task 2 behaves the same way but toggles GPIOG pin 14 and sets task 0 2-bit. Task 3 is similar, but here we simulate a failure between the 4th and 9th iteration. In that period, it won't set its event bit, mimicking a stuck or crashed task. After the 12th iteration, the counter resets to 0. Finally, the watchdog task waits for all event bits using xEventGroupWaitBits. If all bits are set within the 2-second timeout, it confirms all tasks are running. Otherwise, it prints which task has failed. Okay, let's build the code. Here is an error saying that the bits are not constant. That's because the event bits must be compile time constants. So set those to constants. Okay, build it again. Fine, this time no error. So good to go. Let's debug the code. Alright, I've opened the logic analyzer and the serial console, so let's continue. Here you can see from the logic analyzer and the serial monitor that the tasks are running. Now let's analyze the output and what it tells us. Okay, I've added markers to the logic analyzer trace and comments to the serial console output, so let's analyze what they show together. At the beginning, when task 3 count is between 0 and 3, all 3 tasks are setting their bits as expected. The watchdog detects all bits are set within the 2-second timeout, so the log shows all tasks are running. When the count reaches 4, task 3 skips setting its bit. At this point, the watchdog is still waiting for all the bits to be set, so there's no immediate message in the log. By the time the timeout expires at count equals 5, task 3's bit is still missing. The watchdog then reports, task 3 is not running. The same behavior repeats for counts 6 to 9. Since task 3 continues to skip setting its bit, the watchdog repeatedly times out and reports the failure message after every 2 seconds. Finally, when task 03 reaches count equals 10, it resumes setting its bit again. Now the watchdog receives all 3 bits before the timeout and prints, all tasks are running. This behavior clearly demonstrates how the watchdog task uses event groups to monitor multiple tasks. If any task fails to set its bit within the expected time window, the watchdog immediately detects it and reports the issue, a simple but effective task health monitoring mechanism. Now let's look at the event group sync example. Here xEvent group sync stay as a barrier. All tasks must reach the sync point before any of them continue. We have 3 tasks with the same priority and no watchdog task in this example. In task 1 loop first calls xEvent group sync to set its bit and wait for the other 2 bits. It waits up to 2 seconds for the other tasks to join the sync. Then toggles PG13. If all bits are set within the timeout. Task 1 prints, task 1, all tasks synchronized. Otherwise it prints, task 1, synchronization timeout. After the sync attempt it delays 1 second before the next cycle. Task 2 does the same behavior, set the task 2 bit, toggle PG14. and waits 1 second before the next cycle. In task 3, here we simulate a problem. When its internal counter is between 3 and 6, it intentionally skips calling X event group sync and prints a message, task 3, missed sync, indicating the failure simulation. Outside that window it participates in the sync like the others and toggles PG11. Task 3 also waits 1 second between cycles. Okay, let's run the code. Here you can see the task running and the serial monitor print out the result. Let's analyze the results using the time chart and the console messages. I've added visual indicators to make it easier to follow how each task behaves during the synchronization cycles. At the very beginning, all 3 tasks reach the synchronization barrier successfully. The event group releases them together, and we can see T1, T2, and T3 GPIO toggles are aligned on the chart. At 1 and 2 seconds. Again, all 3 tasks reach the sync point and are released together. The GPIO toggles align exactly like the previous cycle. Count value between 3 to 6. Task 3 simulates a failure and skips calling X event group sync. You can see tasks 3 not toggle the its pin. Tasks 1 and 2 block and wait for task 3's bit. At count value is 5. Since task 3 didn't participate again within the 2 seconds time gap, task 1 and task 2 reach the timeout. You can see that task 1 and task 2 pins are toggled here. At count equals 6, task 3 again skips synchronization. At count equals 7, now task 3 calls X event group sync again. All 3 tasks are released together. You can see the GPIO toggles realign just like at the beginning. At count equals 8. Same normal behavior again, stable synchronization across all tasks. So you can see this pattern continuous. Here in the UART output, you will notice, messages are not always printed from all task cycle. Since all tasks run at the same priority and share the same UART resource, sometimes a message may be skipped. This is just a demonstration, and in a real application, you should use proper resource protection like mutex or a dedicated logging task. Otherwise, you'll see inconsistent UART output like this. Okay, let's look at the ISR example. To use event groups from an ISR, there are a couple of RTOS features we must enable first. I also explained it at the beginning of the video. Because the timer daemon task is used to safely defer work from an ISR to a task context. One of the helper APIs, xTimerPen function call, depends on the timer infrastructure to run the deferred function outside the interrupt. So if you want to schedule work from an ISR, you need the timer service enabled. Second, enable the ISR safe event group API and the ISR to task pen function in the include parameters. Those are xTimerPen function call and xEventGroup set bits from ISR. If you open your FreeRTOS config.h file, you'll see these settings reflected there, for example config use timers and the macros that enable the ISR safe API prototypes. If you didn't enable them in CubeMX at the start, you can always add them manually in FreeRTOS config.h. In fact, it's good practice to review and maintain FreeRTOS config.h by manually so you know exactly which kernel features are compiled into your project. Alright, with those kernel options enabled, let's look at the code that uses the ISR safe event group calls. Here only one task waits for the ISR bit. The ISR bit is set from the external GPIO interrupt service routine. Just like in the other ISR examples we've covered in previous videos, we'll follow the same pattern here. When the push button is pressed, the interrupt is triggered, and the ISR sets the event bit. To indicate the ISR, pin 14 toggles. And here in the task 1 if ISR bit sets, pin 13 toggles. Okay, let's run the code. As you can see in the logic analyzer, when the push button ISR occurs, task 01 also toggles GPIO pin 13. This confirms that the event group bit is successfully passed from the ISR to the task. If the ISR does not occur within the timeout period, Task 01 prints a timeout message. This is how we can use event groups together with interrupt service routines in FreeRTOS. It's a clean and efficient way to synchronize external events with tasks. This is it for today's video. We learned how to use event groups together with interrupt service routines in FreeRTOS. In the next video, we'll discuss direct-to-task notifications, another powerful synchronization primitive in FreeRTOS. So stay tuned and don't forget to subscribe. See you in the next video.